Welcome to Loops and Loops, your portal to the world of narrow artificial intelligence. Join us as we embark on a journey through the fascinating realm where artificial intelligence specializes in specific tasks. From image recognition to language translation, narrow artificial intelligence systems excel at solving well-defined problems with precision and efficiency. Whether you're an artificial intelligence enthusiast or just curious about the latest advancements in technology, you're in for an enlightening experience. So buckle up, expand your understanding, and let's unravel the intricacies of narrow artificial intelligence together. Narrow artificial intelligence, often referred to as weak artificial intelligence, is designed to perform a specific task or set of tasks, exhibiting a narrow range of abilities within a limited context. Unlike general artificial intelligence, which aims to mimic human cognitive abilities across a wide range of tasks, narrow artificial intelligence is more specialized and focused. Picture it like a highly skilled worker in a factory excelling at one particular job, but not capable of performing tasks outside of its designated role. These systems are trained to excel at their specific tasks through a process called machine learning. During training, the artificial intelligence is exposed to vast amounts of data relevant to its function. This data serves as the foundation for the artificial intelligence to learn patterns, correlations, and rules that guide its decision-making process. Through iterative exposure to new data and feedback mechanisms, such as reinforcement learning or supervised learning, the artificial intelligence refines its algorithms to improve performance over time. Examples of narrow artificial intelligence applications are ubiquitous in our daily lives. From personalized recommendations on streaming platforms like Netflix or Spotify to virtual assistants such as Amazon's Alexa or Apple's Siri, narrow artificial intelligence enhances user experiences and streamlines tasks. Additionally, spam filters and email services, facial recognition technology in smartphones, and predictive text on keyboards are all examples of narrow artificial intelligence at work, demonstrating its versatility and practical utility. The characteristic features of narrow artificial intelligence systems include their specificity, dependence on large data sets, and lack of general intelligence. These systems excel at their designated tasks but lack the adaptability and creativity of human intelligence. Furthermore, narrow artificial intelligence relies heavily on data availability and quality. Without sufficient training data, the performance of these systems may suffer, highlighting the importance of robust data collection and pre-processing methods. Data processing and analysis are fundamental to the functioning of narrow artificial intelligence systems. These systems ingest vast amounts of data, process it through various algorithms to extract meaningful patterns or insights, and utilize these findings to make decisions or predictions. Techniques such as statistical analysis, pattern recognition, and machine learning algorithms form the backbone of data processing in narrow artificial intelligence, enabling the system to derive actionable intelligence from raw data inputs. Machine learning techniques play a pivotal role in the development and refinement of narrow artificial intelligence systems. By leveraging algorithms that allow the artificial intelligence to learn from experience and improve its performance over time, developers can create more sophisticated and effective artificial intelligence solutions. Supervised learning and reinforcement learning are common approaches used in narrow artificial intelligence development, each offering distinct advantages depending on the nature of the task at hand. Despite their efficacy in specific domains, narrow artificial intelligence systems have inherent limitations compared to general artificial intelligence. These limitations primarily stem from their narrow focus and lack of adaptability beyond predefined tasks. While narrow artificial intelligence excels at tasks it's been trained for, it struggles with tasks outside its expertise, lacking the ability to generalize knowledge or learn new skills autonomously. Narrow artificial intelligence systems can learn and adapt within the scope of their designated tasks. Through continuous exposure to new data and feedback mechanisms, these systems can refine their algorithms and improve performance over time. However, their adaptability is limited to the specific task or tasks they've been trained for, lacking the versatility and cognitive flexibility of human intelligence. Various algorithms are employed in narrow artificial intelligence systems to facilitate decision-making and prediction. Neural networks, decision trees, support vector machines, and Bayesian networks are among the commonly used algorithms, each suited to different types of tasks and data characteristics. These algorithms process input data, identify patterns or relationships, and generate output predictions or decisions based on learned parameters and rules. Industries across diverse sectors benefit from the application of narrow artificial intelligence technologies. From healthcare and finance to retail and manufacturing, narrow artificial intelligence solutions enhance efficiency, productivity, and decision-making processes. For instance, in healthcare, artificial intelligence-powered diagnostic systems assist medical professionals in interpreting medical images and identifying potential health risks. While in finance, artificial intelligence algorithms analyze market data to inform investment strategies and detect fraudulent activities. Interpreting and understanding data inputs are central to the functioning of narrow artificial intelligence systems. These systems employ various techniques, including natural language processing, computer vision, and sensor data analysis, to extract relevant information from diverse data sources. By processing and interpreting data inputs effectively, narrow artificial intelligence systems can generate actionable insights and facilitate informed decision-making across a wide range of applications. Ethical considerations abound in the development and deployment of narrow artificial intelligence systems. Concerns related to privacy, fairness, accountability, and bias must be addressed to ensure that artificial intelligence technologies benefit society without causing harm or perpetuating inequalities. Developers must implement measures to mitigate biases in training data, ensure transparency and explainability in artificial intelligence decision-making processes, and adhere to ethical guidelines and regulatory frameworks to uphold the responsible and ethical use of artificial intelligence technologies. Handling uncertainty and variability in data poses significant challenges for narrow artificial intelligence systems. Real-world data often exhibit noise, incompleteness, and ambiguity, which can undermine the reliability and accuracy of artificial intelligence predictions or decisions. Techniques such as uncertainty quantification, probabilistic modeling, and ensemble methods are employed to address these challenges, enabling artificial intelligence systems to account for uncertainty and variability in data and make more robust and reliable predictions. Developers face a myriad of challenges when creating narrow artificial intelligence solutions. These challenges include sourcing and pre-processing large and diverse data sets, selecting appropriate algorithms and techniques for specific tasks, optimizing model performance and scalability, addressing ethical and regulatory considerations, and ensuring the robustness and reliability of artificial intelligence systems in real-world environments. Collaboration across multidisciplinary teams, ongoing research and development efforts, and adherence to best practices and standards are essential for overcoming these challenges and advancing the field of narrow artificial intelligence. Narrow artificial intelligence systems process natural language inputs using techniques like natural language processing. These systems break down sentences into smaller parts, analyze the meaning of words, and understand context to generate appropriate responses. The key components of a narrow artificial intelligence system architecture include data input modules, processing algorithms, decision-making modules, and output interfaces. These components work together to process data, make decisions, and produce desired outputs. Narrow artificial intelligence systems can interact with humans in natural language. Virtual assistants like Siri, Alexa, and chatbots are examples of narrow artificial intelligence systems capable of understanding and responding to human language inputs. Narrow artificial intelligence systems handle image recognition tasks by analyzing pixel data from images and comparing patterns to pre-existing templates or training data. Techniques like convolutional neural networks are commonly used for this purpose. Using narrow artificial intelligence in data analysis raises privacy concerns as it involves analysing potentially sensitive information. Proper data anonymization, encryption, and compliance with privacy regulations are crucial to mitigate these risks. Narrow artificial intelligence systems perform pattern recognition tasks by identifying recurring patterns or trends in data. Machine learning algorithms such as support vector machines or decision trees are often employed for pattern recognition tasks. Data labeling is essential in training narrow artificial intelligence models as it provides ground truth annotations for supervised learning. It involves manually categorizing or tagging data to teach the artificial intelligence what to look for in future instances. Narrow artificial intelligence systems handle feedback and corrections by incorporating them into their learning algorithms. This helps them improve their performance over time based on user interactions and feedback. Real-world examples of narrow artificial intelligence improving efficiency and productivity include personalized recommendation systems in e-commerce, fraud detection algorithms in banking, and predictive maintenance systems in manufacturing. Narrow artificial intelligence systems handle large-scale data processing tasks by utilizing distributed computing frameworks. These frameworks enable parallel processing of data across multiple nodes to expedite computation. Techniques used to evaluate the performance of narrow artificial intelligence algorithms include metrics such as accuracy, precision, recall, and F1 score. Cross-validation and confusion matrices are also commonly employed for performance assessment. Narrow artificial intelligence systems can generate new insights from data analysis by uncovering hidden patterns, correlations, or trends that may not be apparent to human analysts. Narrow artificial intelligence systems handle unstructured data by employing techniques like text mining, sentiment analysis, or topic modeling to extract meaningful information from text, images, or other unstructured formats. Bias in narrow artificial intelligence algorithms can lead to unfair or discriminatory outcomes. Risks associated with bias include perpetuating existing inequalities, undermining trust in artificial intelligence systems, and causing harm to affected individuals or groups. Narrow artificial intelligence systems handle feature selection and extraction by identifying relevant features from raw data inputs and transforming them into a format suitable for analysis. Techniques like principal component analysis or feature engineering are commonly used for this purpose. Challenges in scaling narrow artificial intelligence solution. To handle big data include managing computational resources, optimizing algorithms for efficiency, and ensuring scalability without sacrificing performance or accuracy. Narrow artificial intelligence systems handle noisy or incomplete data inputs by employing techniques like data cleaning, imputation, or filtering to pre-process the data and remove or mitigate the effects of noise or missing values. Domain expertise is crucial in developing narrow artificial intelligence solutions as it provides insights into the specific requirements, nuances, and constraints of the application domain. Domain experts contribute to defining relevant features, selecting appropriate algorithms, and interpreting results effectively. Narrow artificial intelligence systems handle real-time data processing requirements by employing efficient algorithms, parallel processing techniques, and stream processing frameworks to analyze and respond to data inputs in near real time. Considerations when deploying narrow artificial intelligence in safety-critical applications include rigorous testing and validation, adherence to regulatory standards and safety protocols. and implementing fail-safe mechanisms or redundancy measures to mitigate risks of system failure or malfunction. Narrow artificial intelligence systems handle data security and protection by implementing encryption, access control, and data anonymization techniques to safeguard sensitive information and prevent unauthorized access or data breaches. Techniques for improving the interpretability of narrow artificial intelligence models include feature importance analysis, model visualization, and generating human-readable explanations or justifications for model predictions or decisions. Narrow artificial intelligence systems handle time series. Data analysis by employing specialized algorithms like recurrent neural networks or autoregressive models to capture temporal dependencies and patterns in sequential data. Data augmentation plays a role in improving the performance of narrow artificial intelligence models by increasing the diversity and quantity of training data. Techniques such as data synthesis, transformation, or perturbation help expose the model to a wider range of scenarios and improve generalization. Narrow artificial intelligence systems handle anomaly detection tasks by identifying deviations or outliers from expected patterns in data. Techniques such as statistical modeling, clustering, or machine learning algorithms are used to detect and classify anomalies. Narrow artificial intelligence systems can detect and mitigate adversarial attacks by incorporating robustness techniques such as adversarial training, input perturbation, or defensive distillation to improve resilience against malicious input manipulations. Handling imbalanced data sets is a challenge for narrow artificial intelligence systems, as it can lead to biased model predictions or inaccurate performance evaluation. Techniques such as resampling, cost-sensitive learning, or ensemble methods are employed to address class imbalance and improve model fairness and effectiveness. Deploying narrow artificial intelligence solutions in resource-constrained environments presents challenges such as limited computational power, memory, or bandwidth. Optimization techniques, model compression, and edge computing strategies are utilized to overcome these constraints and enable efficient deployment of artificial intelligence solutions. Narrow artificial intelligence systems handle data streaming and real-time analytics by leveraging stream processing frameworks like Apache Kafka or ApacheLink to ingest, process, and analyze data continuously as it flows through the system. Transfer learning plays a role in improving the performance of narrow artificial intelligence models by transferring knowledge learned from one task or domain to another. Pre-trained models or feature representations are fine-tuned or adapted to new tasks with limited labeled data, accelerating model training and improving generalization performance. Narrow artificial intelligence systems handle data pre-processing and normalization by cleaning, transforming, and standardizing raw data inputs to make them suitable for analysis. This includes tasks like removing outliers, scaling features to a common range, and handling missing values to ensure data quality and consistency. Techniques to reduce the computational complexity of narrow artificial intelligence algorithms include algorithmic optimizations, model simplification, and dimensionality reduction methods such as principal component analysis or feature selection techniques. These approaches help streamline computations and improve efficiency without sacrificing model performance. Handling temporal and spatial data correlations involves analyzing the relationships between data points across time or space. Narrow artificial intelligence systems employ specialized algorithms like recurrent neural networks for temporal data and spatial modeling techniques for spatial data to capture these correlations and make accurate predictions or decisions. Narrow artificial intelligence systems can integrate with existing software and infrastructure through APIs, libraries, or software development kits that allow seamless communication and interoperability with other systems. This enables organizations to leverage artificial intelligence capabilities within their existing workflows and applications. Explainability plays a crucial role in building trust in narrow artificial intelligence systems by providing insights into how the artificial intelligence makes decisions or predictions. Techniques such as model interpretation, feature importance analysis, and generating human-readable explanations help users understand and trust artificial intelligence-driven decisions. Narrow artificial intelligence systems handle regression tasks by predicting continuous numerical values and classification tasks by categorizing data into predefined classes or labels. Techniques like linear regression, logistic regression, and support vector machines are commonly used for these tasks. Optimizing hyperparameters in narrow artificial intelligence models involves tuning model parameters and settings to maximize performance metrics such as accuracy or efficiency. Techniques like grid search, random search, or Bayesian optimization are used to search for optimal hyperparameter configurations. Feature engineering and selection are critical in narrow artificial intelligence model development to identify relevant features that contribute to predictive performance. Techniques such as feature scaling, dimensionality reduction, or creating new features from existing ones help improve model accuracy and efficiency. Narrow artificial intelligence systems can adapt to changes in data distribution over time through techniques like online learning or concept drift detection. These approaches enable the artificial intelligence to continuously update its model based on incoming data streams and adjust to evolving patterns or trends. Handling missing data in narrow artificial intelligence. Models involves imputation methods such as mean imputation, median imputation, or predictive modeling to estimate missing values based on available data. These techniques help prevent bias and ensure robust model performance. Narrow artificial intelligence systems handle model training and inference on distributed systems by parallelizing computations across multiple nodes or processors. Distributed frameworks like TensorFlow or PyTorch enable scalable and efficient training and deployment of artificial intelligence models on distributed architectures. Uncertainty quantification in narrow artificial intelligence applications involves estimating the uncertainty associated with model predictions or decisions. Techniques like probabilistic modeling, Bayesian inference, or Monte Carlo sampling help quantify and account for uncertainty in artificial intelligence-driven outcomes. Narrow artificial intelligence systems handle sequential decision-making tasks by employing reinforcement learning techniques such as Markov decision processes or deep Q learning. These approaches enable the artificial intelligence to learn optimal action sequences in dynamic environments to achieve desired goals. Techniques to reduce overfitting in narrow artificial intelligence models include regularization methods like L1 or L2 regularization, dropout, or early stopping. These techniques help prevent the model from memorizing noise in the training data and improve its generalization performance. Narrow artificial intelligence systems handle multimodal data inputs by integrating information from multiple sources or modalities such as text, images, or sensor data. Techniques like fusion methods, multitask learning, or attention mechanisms are used to combine and process diverse data inputs effectively. Narrow artificial intelligence systems can learn from unlabeled data through techniques like unsupervised learning. Instead of relying on labeled examples, these systems identify patterns, clusters, or relationships within the data to uncover underlying structures and insights autonomously. Reinforcement learning plays a crucial role in training narrow artificial intelligence agents by enabling them to learn optimal behaviors through trial and error. Agents receive feedback in the form of rewards or penalties based on their actions, allowing them to learn from experience and improve their decision-making over time. Narrow artificial intelligence systems handle temporal dependencies in data sequences by employing specialized algorithms like recurrent neural networks or long short-term memory networks. These architectures are designed to capture sequential information and learn patterns across time steps in data sequences. Techniques for improving the scalability of narrow artificial intelligence solutions include distributed computing frameworks, parallel processing techniques, and model optimization strategies. These approaches enable efficient utilization of computational resources and facilitate the deployment of artificial intelligence solutions at scale. Narrow artificial intelligence systems address data drift and concept drift by continuously monitoring incoming data streams and adapting their models accordingly. Techniques like online learning, adaptive algorithms, and change detection methods help detect and mitigate shifts in data distribution or underlying concepts over time. Narrow artificial intelligence systems can perform feature extraction automatically through techniques like deep learning. Deep neural networks can learn hierarchical representations of raw data, automatically extracting relevant features for subsequent analysis or decision-making tasks. Model ensembling plays a role in improving the robustness of narrow artificial intelligence solutions by combining predictions from multiple individual models to make more accurate and reliable decisions. Techniques like bagging boosting or stacking are commonly used to create ensembles of diverse models that complement each other's strengths and weaknesses. Narrow artificial intelligence systems handle data transformation and normalization by pre-processing raw data, inputs to standardize or scale them to a common range. This helps ensure consistency and comparability across different features and improves the performance of artificial intelligence models. Techniques to address the cold start problem in narrow artificial intelligence applications include hybrid approaches, transfer learning, or leveraging auxiliary information to bootstrap the learning process. These techniques help overcome the lack of initial data or knowledge and accelerate model training. Narrow artificial intelligence systems handle batch processing and streaming data by employing specialized frameworks and algorithms for each scenario. Batch processing involves analyzing fixed batches of data offline, while streaming data processing involves analyzing data in real time as it arrives. Narrow artificial intelligence systems can perform unsupervised learning tasks to uncover patterns, clusters, or associations within data without labeled examples. Techniques like clustering, dimensionality reduction, or association rule mining are used for unsupervised learning tasks. Domain adaptation plays a role in transferring knowledge between domains in narrow artificial intelligence by adapting models trained on source domain data to perform well on target domain data. Techniques like domain alignment, adversarial training, or transfer learning are used to bridge the gap between different domains. Narrow artificial intelligence systems handle noise and outliers in data by employing techniques like robust statistics, outlier detection methods, or data pre-processing steps such as filtering or smoothing. These techniques help improve the quality and reliability of artificial intelligence-driven decisions or predictions. Techniques for improving the efficiency of narrow artificial intelligence algorithms include algorithmic optimizations, model pruning, or hardware acceleration. These approaches help reduce computational overhead and speed up the training or inference process. Narrow artificial intelligence systems handle privacy-preserving data analysis by implementing techniques like differential privacy, federated learning, or homomorphic encryption to protect sensitive information while still deriving useful insights from. These techniques help balance the trade-off between data privacy and utility in artificial intelligence-driven applications. Model compression plays a crucial role in reducing the memory footprint of narrow artificial intelligence models by optimizing model parameters, reducing redundancy, or using specialized compression techniques. This enables efficient deployment of artificial intelligence models on resource-constrained devices or environments without sacrificing performance. Narrow artificial intelligence systems handle data augmentation and synthesis by generating additional training examples through techniques like image rotation, flipping, or adding noise to text data. These approaches help increase the diversity and quantity of training data, improving the generalization and robustness of artificial intelligence models. Narrow artificial intelligence systems can detect and handle concept drift in data streams by continuously monitoring data distributions and adapting their models accordingly. Techniques like change detection algorithms or drift detection methods help detect shifts in data patterns and trigger model updates or retraining as needed. Techniques for improving the robustness of narrow artificial intelligence models to adversarial attacks include adversarial training, input perturbation, or robust optimization methods. These approaches help defend against malicious input manipulations and improve model resilience to adversarial perturbations. Narrow artificial intelligence systems handle data exploration and visualization by employing techniques like descriptive statistics, scatter plots, or heat maps to analyze and visualize data distributions, correlations, or trends. This helps users gain insights into the underlying characteristics of the data and inform subsequent modeling or decision-making processes. Active learning plays a role in optimizing the data labeling process for narrow artificial intelligence models by selecting the most informative or uncertain data points for annotation. This reduces the labeling effort while maximizing the effectiveness of the training data, leading to more efficient model training and improved performance. Narrow artificial intelligence systems handle multitask learning scenarios by jointly training a single model to perform multiple related tasks simultaneously. This enables shared learning of task-specific features and relationships, leading to improved generalization and efficiency across tasks. Narrow artificial intelligence systems can adapt to changes in the environment or task requirements through techniques like transfer learning, continual learning, or online adaptation. These approaches enable the artificial intelligence to update its knowledge or adapt its behavior based on new data or evolving circumstances. Techniques for quantifying and mitigating bias in narrow artificial intelligence models include fairness-aware algorithms, bias detection methods, or fairness constraints during model training. These approaches help identify and mitigate biases in artificial intelligence-driven decisions or predictions, promoting fairness and equity in artificial intelligence applications. Narrow artificial intelligence systems handle hierarchical and relational data structures by employing techniques like graph neural networks, relational learning algorithms, or hierarchical clustering methods. These approaches enable effective modeling and analysis of complex data structures with interconnected or nested relationships. Uncertainty estimation plays a crucial role in decision-making with narrow artificial intelligence models by quantifying the confidence or uncertainty associated with model predictions. Techniques like probabilistic modeling, uncertainty quantification, or Bayesian inference help users make informed decisions or take appropriate actions based on artificial intelligence-driven predictions. Narrow artificial intelligence systems handle distributed training across multiple devices or nodes by partitioning data and computations, synchronizing model updates, or employing decentralized optimization algorithms. These approaches enable efficient parallelization of model training and scaling to large datasets or computational resources. Narrow artificial intelligence systems can perform automated feature selection and dimensionality reduction through techniques like feature importance analysis, principal component analysis, or autoencoders. These approaches help identify relevant features and reduce the dimensionality of input data, improving model efficiency and generalization performance. Techniques for improving the interpretability of narrow artificial intelligence. Models include feature importance analysis, model visualization, or generating human-readable explanations for model predictions. These approaches help users understand and trust artificial intelligence-driven decisions, promoting transparency and accountability in artificial intelligence applications. Narrow artificial intelligence systems handle model evaluation and validation by assessing performance metrics like accuracy, precision, recall, or F1 score using techniques like cross-validation, holdout validation, or bootstrapping. These approaches help ensure the reliability and effectiveness of artificial intelligence models in real-world applications. Hyperparameter tuning plays a crucial role in optimizing the performance of narrow artificial intelligence models by adjusting parameters that control the learning process, such as learning rates or regularization strengths. This helps fine-tune the model to achieve better accuracy, generalization, and efficiency. Narrow artificial intelligence systems handle data labeling and annotation tasks by utilizing human annotators or crowdsourcing platforms to label data examples with relevant tags or categories. This labeled data is then used to train artificial intelligence models through supervised learning. Narrow artificial intelligence systems can handle semi-supervised and self-supervised learning tasks where only a subset of the data is labeled or no labels are provided at all. Techniques like self-training, pseudo-labeling, or generative models enable artificial intelligence systems to leverage unlabeled data to improve performance. Techniques for improving the efficiency of narrow artificial intelligence inference include model quantization, pruning, or compression to reduce the computational resources required for model execution. These approaches help deploy artificial intelligence models on resource-constrained devices or environments without sacrificing performance. Narrow artificial intelligence systems handle explainable and interpretable decision-making by generating human-readable explanations or justifications for model predictions or decisions. Techniques like feature importance analysis, model visualization, or rule-based explanations help users understand and trust artificial intelligence-driven outcomes. Probabilistic reasoning plays a role in narrow artificial intelligence applications by quantifying uncertainty and reasoning under uncertainty using probabilistic models or inference algorithms. This enables artificial intelligence systems to make more informed decisions or predictions in uncertain or ambiguous situations. These systems handle temporal and spatial data correlations by employing specialized algorithms like recurrent neural networks or convolutional neural networks. These architectures are designed to capture sequential and spatial dependencies in data, enabling accurate predictions or classifications. Narrow artificial intelligence systems can perform online and incremental learning by updating model parameters continuously as new data becomes available. This enables artificial intelligence systems to adapt to changes in the environment or task requirements without retraining the entire model from scratch. Techniques for optimizing the memory usage of narrow artificial intelligence models include model compression, parameter sharing, or sparse representations to reduce the memory footprint of model parameters or activations. This enables efficient deployment of artificial intelligence models on memory-constrained devices or platforms. Narrow artificial intelligence systems handle uncertainty and variability in data by employing techniques like uncertainty quantification, robust statistics, or ensemble methods to account for and mitigate uncertainty in artificial intelligence-driven decisions or predictions. Interpretability plays a crucial role in ensuring the trustworthiness of narrow artificial intelligence models by providing insights into how the model operates and why it makes certain predictions or decisions. Transparent and interpretable models help users understand and trust artificial intelligence-driven outcomes, promoting accountability and fairness. Narrow artificial intelligence systems handle class imbalance and rare events in data by employing techniques like oversampling, undersampling, or cost-sensitive learning to balance class distributions and improve model performance on minority classes. Narrow artificial intelligence systems can handle multimodal and heterogeneous data inputs by integrating information from multiple sources or modalities such as text, images, or sensor data. Techniques like fusion methods, multitask learning, or attention mechanisms enable effective processing and analysis of diverse data inputs. Techniques for improving the robustness of narrow artificial intelligence models to adversarial attacks include adversarial training, input sanitization, or robust optimization methods. These approaches help defend against malicious input manipulations and improve model resilience to adversarial perturbations. Narrow artificial intelligence systems handle data privacy and security concerns by implementing techniques like data anonymization, encryption, or access control to protect sensitive information and prevent unauthorized access or data breaches. These measures help ensure the confidentiality and integrity of data in artificial intelligence-driven applications. Data preprocessing and feature engineering play essential roles in narrow artificial intelligence model development by preparing raw data inputs for analysis and extracting relevant features that capture important information. Preprocessing involves tasks like cleaning, scaling, and encoding data to ensure consistency and compatibility, while feature engineering involves creating new features or transforming existing ones to improve model performance and accuracy. Narrow artificial intelligence systems handle concept drift and data evolution over time by continuously monitoring data streams and adapting their models accordingly. Techniques like online learning, adaptive algorithms, or change detection methods help detect shifts in data patterns and trigger model updates or retraining as needed. Narrow artificial intelligence systems can perform anomaly detection and outlier identification tasks by analyzing data patterns and identifying instances that deviate significantly from expected behavior. Techniques like statistical modeling, clustering, or machine learning algorithms are used for anomaly detection in various domains. Techniques for improving the interpretability of narrow artificial intelligence models include model visualization, feature importance analysis, or generating human-readable explanations for model predictions. Narrow artificial intelligence systems handle uncertainty and variability in data inputs by employing techniques like uncertainty quantification, robust statistics, or ensemble methods to account for and mitigate uncertainty in artificial intelligence-driven decisions or predictions. Narrow artificial intelligence systems handle data storage and retrieval in resource-constrained environments by using efficient data structures, compression techniques, or streaming data processing frameworks to minimize memory usage and optimize performance. Model distillation is a process where a large, complex model, which is teacher model, transfers its knowledge to a smaller, simpler model, which is student model, through supervised learning. This helps compress the knowledge of the teacher model into a more lightweight student model, making it suitable for deployment in resource-constrained environments typical of narrow artificial intelligence applications. Strategies for optimizing memory usage in time series forecasting models include using sparse representations, model compression techniques, or incremental learning approaches to reduce memory footprint while preserving model accuracy and performance. As we wrap up today's exploration of narrow artificial intelligence, we hope you've gained valuable insights into the capabilities and limitations of specialized artificial intelligence systems. Remember to like, share, and subscribe to Loops and Loops for more engaging content on the frontiers of artificial intelligence technology. Let's continue to push the boundaries of what narrow artificial intelligence can achieve and harness its potential for the betterment of society. Until next time, keep those loops tight, keep learning, and keep advancing the field of artificial intelligence. Thank you for joining us on this enlightening journey.